I'm Kathryn Nguyen, Kathryn Nguyen, and I represent the project on a comparison of various methods to inactivate granulocyte-macrophage quality stimulating factor, also known as GM-CSF, in CAR T cell chimeric antigen receptor therapy. For some patients, CAR T cell therapy is the last option resort when traditional methods such as chemotherapy and radiation show no effect. However, over time, after the treatment was administered, the body began to reject the therapy and some negative side effects such as toxicity or show. To make the right answer question, using a literature review, what research has been from time of potential to provide safer cancer immunotherapy treatment? We might ask you, what exactly are CAR T cells? CAR T cells are a type of immunotherapy of cancer treatment that uses your body's own immune cells to fight the disease. Your immune system is comprised of two main components. The first is your innate immune system, which you're born with and it's your general response, such as like your skin or your white blood. Your adaptive immune system, which will define our T cells, have a specific response which can fight off certain pathogens. They can also record information of pathogens you had before in order to fight them off in the future. As you can see in this image right here, the T cells have a receptor that has a specific shape which combines precisely. This is why it calls the specific response. They play a large role in CAR T cells. Two components of a CAR T cell are the T cell plus and chimeric antigen receptor, which is also abbreviated as CAR. This has two parts to it. The green portion, also called the antigen receptor. The antigen receptor is important in cell recognition and binding. This allows for the CAR T cells to communicate with the cancer cell. And the blue spot here is the transmembrane domain, which helps the CAR attach itself onto the membrane of the T cell. And this is defined by CAR T cell. In order for patients to receive CAR T cell therapy, first their blood has to be collected, and within a patient's blood, their T cells can be isolated. From these T cells, they will edit it with a CAR gene that can send the CAR back to you. Your final CAR T cell, which will then find a number, it orders for the patient to is going to be injected back into the patient, and will hopefully fight back cancer cells. However, there have been some negatives that have after CAR T cell treatment. First is antigen escape, which is when these CAR T cells are unable to fight against cancer cells, and they go elsewhere in the body. On-target off-tumor effects happen when these CAR T cells fight against your normal cells, which are not cancer, leading to cell death, which can transform the body. The third is trafficking and tumor infiltration. When these CAR T cells are unable to map system cells towards the cancer cells and lead to continued presence of cancer cells in the patient's body. The fourth being CAR T cell associated toxicity, which occur when these CAR T cells bind to the various cells and release cytokines. Cytokines are proteins that are released from the body that request help from the immune system to be set for the area. Which leads me to the main part of my presentation, cytokine release syndrome. This occurs after the CAR T cell has binded to the tumor cell, as you will see on this image, and this releases large amounts of cytokines. While it's important that these cytokines can recruit the cells of your immune system, the hyper-recruitment of the immune cells often causes inflammation. This can manifest the symptoms that are similar to a mild flu and outward organ failure. You'll often see this when you get a cut in your arm and it gets infected. When it gets infected, the cytokines will be released and will then recruit your immune system to send the cells towards your cut. When there are too many immune system cells sent towards it, your cut will get inflamed. Scientists have found that preventing one way to prevent unattended leakage of inactivate GM-CSF, also known as granulocyte-macrophage colony stimulating factor, but I would refer to GM-CSF for the rest of my presentation. On the image on the far right, you can see that a regular CAR T cell, that treat large amounts of cytokines resistant to neural inflammation. However, either after the CAR T cell, after the GM-CSF has been released, they can either be inactivated after or prevented or removed before. This will reduce cytokines and therefore enhance CAR T cell function and neural inflammation. Three methods that, as we discussed, are using antibody internalization, and using short-acting RNA insertion into the target. The first method is using CRISPR to target disease. This paper actually uses antibody internalization to preserve the effects of GM-CSF, and then follow up with the algorithm using CRISPR. On the far right of the image, you can see that there is a blue little small bubble over there. It's an enzyme that contains RNA, a guide RNA. This RNA will then divide the protein into the cell, and it will then bind to a segment of the cell's DNA, which will then cleave a segment that codes to GM-CSF. This will stop GM-CSF from being released by the cell. In the graph on the top right, you can see that GM-CSF has decreased by 60% through this method. The other three graphs show the three other different cytokines that were not inhibited by this effect to support that CRISPR did not induce off-target effect. However, the prevention of these also led to increased CAR T cell function as well as decreased illness. The second method is using an antibody to fight against the GM-CSF. Antibodies are known to capture the effects of GM-CSF, which is why this method was used. In this solution, the first solution, no antibodies were placed in the solution with the CAR T cell, and therefore the GM-CSF was able to continue its activity, as seen by the green triangles that have not had antibodies found to them. In the second solution, the antibodies have been taken the position and have decreased the activity of GM-CSF, which helps prevent cytokine release as well as possible neuroinflammation. The third method is using a short surface RNA. A short surface RNA will be processed in the cell associated with what is larger than the circle, and will then be released into the cytoplasm of the CAR T cell. Here, the short-handed RNA will then be edited to a microRNA, which has two strands, but only one strand will bind to a complementary strand on the mRNA, where it will then inactivate. The gene that codes for GM-CSF. As you can see, as the solution on the right, there is a higher amount of GM-CSF, as you can see by the purple triangle. However, there is a 89 to 98.9% decrease in GM-CSF after the short-term RNA insertion in the second solution. In conclusion, using antibodies is much more feasible and predictable. This method, like CRISPR and short-term RNA and general gene editing techniques, have often been urged to be used cautiously since they often can lead to off-target effects. CAR T cells and cytokines have a very complex relationship, as you can see by this image here. There are many different cells that release cytokines, and we're still unsure of which cytokines actually cause cytokine release syndrome. And GM-CSF is one of many cytokines that trigger. Finally, currently CAR T cells are only able to treat blood cancer and not solid tumors like breast and lung cancer. However, there is so much progress in this therapy. Some future research questions and statements are: how exactly does cytokine calculus into body? How does these individuals move the conflict in CAR T cell therapy? And how will we use the body drugs to move to assess the distribution? Some next steps to be taken are testing these methods on nuts or some other route. So my lesson is